Dear colleagues, my name is Rustam Yarullin. I am from Kazan Scientific Center of Russian Academy of Sciences. My co-authors are Professor Valery Shlyannikov, Professor Roberto Citarella, and PhD student Daniele Amato from University of Salerno. The title of my talk is Mixed Mode Surface Crack Growth in Aluminum Alloys under Complex Stress State. The outline of my talk is the following. First of all will be introduction. Then I'm going to show you the results of experimental study, which consists of specimen geometry, test equipment, material properties, and experimental crack path. After that, I'm going to show you the results of numerical study, which include description of finite element models, numerical simulation algorithm, and stress intensity factors distributions. Results and discussion are going to be introduced later. Finally, I'm going to show you conclusions. Some words about motivation of our study. The circular cylindrical metallic components of aircraft structure, power engineering elements, pressure vessel, and piping are subject to complex stress state. In most cases, part flows appear on the free surface of the cylinder and defects are approximately considered as semi-elliptical cracks. The fatigue growth analysis of surface cracks under complex stress states is very important for accurate structural integrity prediction and determination of the residual fatigue life of components. Therefore, fracture resistant parameters at the complex stress state are needed for material selection and design. The subject of this study is cylindrical hollow specimens with semi-elliptical surface cracks. The diameter is equal to 28 mm in the test section and the length is equal to 130 mm. Using electrospark method, initial edge notch was cut with initial depth equal to 3 mm. For this study, we used a specimen with initial aspect ratio equal to 0.3. The geometric parameters of the specimen test section and the growing crack are presented in this figure. The test materials are most popular in aircraft industry: aluminum alloys D16T and B95AT, analog of 2024 and 7075 aluminum. All tests were carried out at room temperature. Type of loading: cyclic tension, cyclic torsion, and cyclic tension torsion. Complex stress state tests were performed by using following equipment: servo-hydraulic test system with capacity ±100 kN and ±2000 Nm. Crack depth and crack length were measured by displacement gauge, crack mouth opening displacement, and optical microscope. The first step of experimental study was a determination of the main mechanical properties of considered alloys. Obtained main elastic and elastic plastic mechanical properties are listed in Table 1. The Paris constants for all alloys are presented in Table 2. You can see that B95AT alloy has higher mechanical properties with reduced fracture resistance properties. The next step of experimental study was crack growth rate tests. The variation of crack growth behavior was studied under cyclic axial tension, pure torsion, and combined tension-torsion fatigue loading with stress ratio 0.1. During each test, the stress ratio was modified from 0.1 to 0.5 for a few cycles in order to create bite marks on the fracture surface. The typical fracture surface of tested specimens is shown in these figures for different loading conditions. From the crack front shape obtained in this manner, the relationship between aspect ratio and the relative crack depth and relative crack length can be obtained for different loading conditions. As mentioned above, the crack growth was monitored by using a combination of the optical microscope and the crack mouth opening displacement for tension and tangent torsion tests. The relationships between crack mouth opening displacement and crack length on the free surface of hollow specimens for both considered aluminum alloys are plotted in these figures. A strong correlation was found between these two parameters for the tension and tension torsion tests, and this information can be very useful for the verification of numerical simulation results under multi-axial stress states. Next part of my talk is concerned with numerical results. The cylindrical specimen has been modeled by Abacus software with nearly 3000 linear hexahedral elements of type C3D8R. The machinery clamps have been replicated by using a kinematic coupling constraint between the specimen external lateral surfaces and two reference points located on the top and the bottom surfaces. Therefore, the boundary conditions and loads have been applied on the reference points. The numerical starting point for the crack propagation simulation is the notch. It is modeled as an ellipse, cutting the specimen orthogonally to its axis and middle height. Frank 3D creates a meshed tube around the crack front. The first tube ring is made up of collapsed hexahedral elements, that is, quarter-point single wedge elements. These are surrounded by king rings of brink elements. Then pyramids on the outer tube provide compatibility between bricks of the tube and tetrahedra of the volume. After the remeshing, the number of elements increases up to around 40,000 and the number of nodes up to 60,000. Numerical simulations have been performed by the synergic use of the software Abacus and Frank 3D. Here one can see an overview of the simulation process. The cylindrical specimen has been modeled by Abacus software. The finite element model includes the material parameters, the boundary conditions, and the initial uncracked mesh. This is the input for the fracture analysis code 3D, Frank 3D. This software divides up the model into two parts, the global and the local. Frank 3D adaptively remeshes an existing finite element model with the inserted crack to generate a cracked model. Each simulation step consists of 3 phases. During the preprocessor phase, the new crack is geometrically inserted into the domain and it is remeshed with quadratic tetrahedral elements. Then the local and the outer global mesh are merged. The second phase is the finite element calculation, during which stresses and displacements are calculated for all nodes. The post-processor phase aims to determine the stress intensity factors for each crack front nodes and extend them towards their propagation direction. The stress intensity factor were computed according to the M-integral formulation. To obtain the M-integral, two solutions are assumed and superposed. Solution 1 is the finite element solution for the problem of interest. Solution 2 is an auxiliary solution. The M-integral formulation comes into form here reported for 3-dimensional case. The domain of integration is a cylinder that encloses a portion of the crack front as illustrated in figure. The equivalent stress intensity factor formulation implemented in Frank 3D is the one shown here, and it gives the possibility to user to calibrate the formula for his own requirements by inserting proper values for gamma 2 and gamma 3. The propagation law is a simple Paris law type with the material constant expressed in tabular form. The classical maximum tangential stress theory was used for the calculation of the kink angle delta theta. This criterion seeks out a mode 1 crack path. In these pictures, the crack size A, B, and C measurement is explained. The picture on the left hand side shows a halfway crack shape before front separation, whereas figure on the right hand side depicts the final crack shape after front separation. Normalized crack front abscissa varies in the range from 0 to 2. 0 means crack front initial point, 2 is the crack front endpoint. In this slide, K1 distribution for pure tensile test is showed for both aluminum alloys. K2 and K3 are practically zero during all propagation steps. Therefore, were not reported. K equivalent has the same K1 distribution. The legend indicates the step which the curve refers to, and F1 and F2 indicates the first of the second front, respectively. Here is the stress intensity factor distribution is showed for D16T in tension-torsion test. Step 5 is the last step before crack front separation, whereas step 6 is the first step after crack front separation. In general, K1 has an increasing tendency, whereas K2 goes quickly to zero as soon as the crack kinks. K3 decreases during all crack propagation. K equivalent reflect the same tendency of K1, except for the step 0, in which K2 and K3 have values comparable to K1. Here, the stress intensity factors distribution is showed for D16T in torsion tests. The first propagation steps were not reported. As in the first propagation step, a very small tensile load was superimposed to the torsional one in order to facilitate the numerical crack propagation. The first step taken into account was step 3, here reported in blue. Step 9 is the last step before crack front separation, whereas step 10 is the first step after crack front separation. Here are displayed the stress intensity factors for aluminum alloy B95AT in tension torsion and pure torsion loading condition. Stress intensity factors reflect the same tendency already showed for aluminum alloy D16T in previous slides. In general, one can appreciate the stress intensity factor symmetry or antisymmetry except for some numerical irregularity. And last part of my talk is results and discussion. These graphs show the comparison between numerical and experimental results. On the left-hand side, the graphs are related to D16T, whereas on the right-hand side, they are related to B95AT. The upper graphs show the crack mouth opening displacement comparison, the middle one the B dimension comparison, and the bottom ones display how the aspect ratio evolves as the crack grows. In general, a better agreement between numerical and experimental results can be seen for alloy D16T. With these graphs, it is shown the comparison between numerical and experimental results in the case of tension torsion tests. Again, the graphs on the left-hand side are related to D16T, whereas they are related to B95AT on the right-hand side. With these loading conditions, the correlation between numerical and experimental data is very high for both materials. Numerical crack mouth opening displacement for D16T is close to experimental data, that is for B95AT. In this slide, the graphs show the comparison between numerical and experimental results in the case of pure torsion tests. In general, it is possible to see a higher crack growth rate in the numerical results with respect to the experimental data. In this slide, the experimental and numerical crack paths are compared in the case of tension torsion and pure torsion loading conditions. The numerical analysis show, as in the experiments, a higher kink angle is in the case of pure torsion loading conditions. The fracture mechanics parameters for the complex stress state, which were obtained at previous part of our study, were used to crack growth rate interpretation. On this slide, you can see the influence of the loading conditions. It is clear that aluminum alloy B95AT is more sensitive to complex stress state. At the same time, the crack growth diagrams for D16T aluminum alloy insignificantly changed as a function of loading conditions. It is known that in the structures with surface defects, the crack front has two specific points. One relates to the intersection of the crack front line with a free surface, and the other is the deepest point of the crack front. On these figures, you can see the crack growth rate as a function of equivalent stress intensity factors for different crack front points and different loading conditions. A significant reduction of the crack growth rate is observed in the direction of the deepest point of the crack front as a function of complex stress state. And conclusions of my talk. Thank you very much for your kind attention.